Here we will discuss mass conservation, but now not at the integral level, at the level of control volume, but at the differential level. And again, we'll start with a derivation. So we'll start from our statement of mass conservation at the control volume level. So this is what we have. And here, remember, this is true for any arbitrary control volume. So this is true. For any arbitrary control volume. I want to really insist for any. I can choose it however I want, as long as it's not changing in time. Those were our assumptions. And this derivation is going to be for the differential level is much more mathematical and much less intuitive than the derivation that we did here at the control volume level. But okay, so let's go. So the first thing we need to do is to look at this. We'll look at this first term, right? And what we're going to do is because this control volume here, so the bounds of this integral are not changing in time, we can bring the time derivative inside of the integral, and it becomes a partial derivative. And we can only do this because our control volume is independent of time. So this first term, when we do this, when we bring the derivative inside of the integral, becomes the integral over the control volume of partial rho partial t dv. Note that once we bring this time derivative inside of the integral, rho is a function of time, but also of the position vector. So it's a function of zero variable. The derivative becomes a partial derivative. Now, this term here So the divergence theorem states, you can write the divergence theorem for any vector field V, right? So let's say I have a vector field V, and it says that the flux of this vector field coming out of a control surface CS is equal to the volume integral of the divergence of this vector field times dV. This is a theorem from calculus. Here, in this case, our vector field is rho u, and therefore we can rewrite this term as the volume integral over CV of the divergence of rho u times dV. And so this term plus that term will be equal to 0. Now that we've changed this second term here into a volume integral, we can rewrite everything as just one big volume integral. So I can write this as the volume integral of d rho dt, partial rho partial t, plus the divergence of rho u times dv, and this has to be equal to 0. And now here we have a volume integral that is equal to 0, and you have to remember that we did this regardless of the bounds of our control volume. And so if an integral of a certain integrand is equal to 0 for any control volume, that means that the integrand itself has to be equal to 0. So this can only be true when the integrand itself is equal to 0. And so from there we can deduce our conservation of mass statement at the differential level, which we write partial rho partial t plus the divergence of rho u is equal to 0. That's one form of mass conservation at the differential level that we can write. Note that this is really a statement at the differential level, not at the integral level. Now we can write this equation in another form using some formulas from calculus. So remember, for functions of one variable, let's say I have a function f and a function g. If I take the derivative of this function, you know that this is equal to the derivative of f times g plus f times the derivative of g. Now you have similar formulas for any differential operator, so the divergence or the gradient or the curl of any sort of product between two fields. Note that this is not really, those are two different fields, a scalar field times a vector field, so it's not really the same as two functions, but you have similar formulas as to these whenever you have a differential operator acting on a product between two fields. And in particular, what you have is that the divergence of rho u is equal to rho times the divergence of u plus u grad rho. And you always want to check the order of your tensors. So here I have 1, right? You have 1 bar. This is order 0, so it's still 1 dot, so minus 1. So this is order 0. This is a scalar, and this is a scalar, and this is a scalar, so that works. And this is a scalar, so I go further, order 1 minus 1, so this is still a scalar. So all of these are okay. And so when I rewrite my divergence of u, I get partial rho partial t plus u grad rho plus rho divergence of u. This is another way of writing mass conservation on the differential volume, because that makes appear a quantity which we discussed before, which is this, which is the material derivative. So partial t plus u grad rho, the material derivative of rho. So this is the material derivative of our vector field rho plus rho divergence of u equals to 0. This is all of these forms, whether this one or that one are equivalent. This is mass conservation at the differential level, and it's also called the continuity equation.